So welcome back. Let's continue on our discussion of a derivation of the Taylor series. So, firstly, I would just like to point out that we can use some other notation to denote x to the power of n falling where the difference is s. So this notation isn't necessarily going to be the best. Firstly, it's not a visual notation, at least not when you put the s here and generalise the falling factorial to whatever difference you want. And also, I think it's going to be easier to see how the series that we're going to create becomes the Taylor series if we use different notation. So remember, this is x times x minus 1. Oh, whoops, sorry, no, it's not that. It's x minus 1s, x minus 2s, all the way down to x minus n minus 1 times s. So we could write this using the multiplication symbol. So as the multiple of x minus rs, where r goes from being equal to 0 to being equal to n minus 1. So clearly when n is equal to, whoops, that's not what I meant to press, this is what I want to press. Clearly when n is equal to 1 here, that is just going to be x to the power of 1. X to the 1 falling, no matter what the difference is just going to be equal to x. And you can imagine, that if n is equal to 0, I know it doesn't really quite work here, but that's going to be equal to 0, sorry, not 0, that's going to be equal to 1. It's the equivalent of x to the power of 0 is equal to 1. X will agree that x to the power of 0 falling is also going to be equal to 1, because then it works out very nicely with regards to this here, because then if we differentiate x to the power of 1 falling, then it's just going to be equal to 1 if x to the power of 0 falling is equal to 1, which of course is the derivative of x. So just some more sort of little points to make about finite derivatives. The derivative with respect to x, where delta x is equal to s of a constant function, is going to be equal to 0. That hopefully is plainly obvious. Graphically, the reason for that is a constant function just looks like that. So of course the change in y is always going to be equal to 0. So the gradient, no matter what the difference is, no matter which position you are at, is always going to be equal to 0. And you could plug this in. A minus a over s is what you get. So you get 0 divided by s, which is just equal to 0, provided s is not equal to 0. So there's something that I hope is plainly obvious. Another thing that I hope is plainly obvious, we've already said it, but the derivative of x with respect to x, and again delta x is equal to an arbitrary s, is just going to be equal to 1, and that, again, just plug it into the function, or the formula, x plus s minus x divided by s, you get 1. And again, the reason graphically for that is no matter what the difference, no matter what the position, the gradient is always going to be equal to 1. Another point, that if you take the finite derivative with respect to x, where delta x is equal to s of a constant term times a function, so if you take a of f of x, then just like in normal calculus, that is a times the derivative with respect to x, as delta x is equal to s of f of x. So constant terms can be pulled out of the differentiation just like in normal calculus. Again, that comes straight from the formulas. So I'm not even going to prove that. I hope you're easily capable of doing that yourself. Another point is that if you take the derivative with respect to x as delta x is equal to s of two functions added together, so f of x plus g of x, then again, just like in normal calculus, that is the derivative with respect to f plus the derivative with respect to of g. Sorry, it's the derivative of f with respect to x as delta x is equal to s plus the derivative of g with respect to x as delta x is equal to s. Again, that comes straight from the formula. Just plug in, this is our function, evaluated at x plus s. It's going to be f of x plus s plus g of x plus s minus the function evaluated at x, which is just f of x, g of x, all divided by s. You can split that up into these two separate bits. And we're not going to go into this, but you can find there is an analogous version of the product rule in calculus of finite differences. It's more complicated. It's not as beautiful as the product rule in normal calculus. We don't need that for our purposes, so we're not going to bother doing it. All we need is these two properties here, this and this. And the chain rule, again, the chain rule is more complicated here than in normal calculus, but again, you can concoct the chain rule. But again, we don't need the chain rule, so we're not going to come up with that either. So, now what we need to discuss then is just the meaning of higher level derivatives, and a discussion of that leads us to finding the Newton series. The Newton series, when you look at it initially, if I wrote it down, you'd think, how on earth are we going to get that? Must be quite a complex process to get at that. But actually, just thinking about the meaning of the higher power derivatives in calculus of finite differences means that you arrive at the Newton series. So this is really quite nice. This is not complicated. So let's just draw a picture. So here is our graph. So this is going to be the y-axis, the x-axis, and we have our function, which we'll just denote like so. So this is f of x. And we'll stick with our notation. So we're going to be talking about a point A. So our series is going to be fixed around that point A, just like if we go back to the original Taylor series, remember the approximation is all centered about some point A. The series is centered about some point A, so the Newton series is also going to be centered around that point A, or the version of the Newton series that we're going to concoct. And as I say again, the notation is not common notation. This is notation that I've made up so that I can draw parallels and it's easier to see it. But you can go on Wikipedia and look up the normal notation for the Newton series. And we're going to be talking about an arbitrary difference of s. So this can be a plus s. So this is our difference here of s. And of course this is f at a plus s. And this is f of a here. So now we know what the first derivative means. It means the gradient of that triangle there. So the change here divided by the change in x, which is obviously s. So this divided by this, the gradient of that triangle, that's the first derivative. And remember that that first derivative, which I'll write in a different way actually now, so that first derivative with a difference of s evaluated at a, if we times that by s, which is the difference in x, remember this is the ratio between the difference in y and the difference in x. So if you times it by the difference in the difference in x, it gives you back the difference in y. So this little change in y here is equal to the first derivative evaluated at that point a times s. So therefore, this point here, this value of f evaluated at a plus s, it is going to be equal to f evaluated at a plus that difference, that change in the y, which is just going to be the derivative evaluated at a times s. Now why am I going into this? Why have I wrote this out? The point is that if you know the value of the function at the point a, and you know the value of the first derivative evaluated at a, then you instantly know the value of the function also. Well, that sets the value of the function at the point a plus s. So why am I stressing this so much? Because this is where the derivation of the Newton series is going to come from. If you have two functions, So let's say we have another little picture up here. If we have two functions, so this can be f of x, and this one here can be g of x. Oops, that didn't go particularly well. Let's draw another one. No, that's not going very well either. So that's better. So let's call this g of x. And let's say this point, and I'm just going to highlight this in red. So this point and this point, you see those 2 points are the points where the function has equal values. And I'm going to use that picture to make a point here. So if this point we called a, and the value of both functions is f of a, and of course g of a is going to be the same because we're talking about that point where they're overlapping. And let's say this difference between those 2 points is s, so this next point here is a plus s, and again s could be anything, so we can do this. And of course those 2 points there, the two functions have the same value there as well, so f at a plus s is the same as g at a plus s. That would mean that both of those functions have to have the same value of the first derivative at a, where the difference is s. So both of them, the first derivative, where the difference is a, at that point s, for the function f would be equal to the first derivative for a difference s at that point a. Now I'm not saying that the derivative, the function, will be the same. Of course it won't, they're completely different functions. But at that, if you evaluate the first derivative of this function, where the difference is s at the point a, it will be equal to the first derivative of this other function with the difference s at that point a. And the reason is, otherwise they wouldn't go through the same points. So it has to be this. Knowing this is equivalent to knowing this. And why am I saying this? Because if you have two functions that have the same value at a point and the same value of the derivative at that point, then that instantly tells you that they both have the same value at the point a plus the difference that the derivative is with respect to. And this is how we're going to build the Newton series. We're going to say, if we want to approximate our function, we just need to create another function that has the same values of finite derivatives, because then it will make more and more points have to be the same. And let me explain more by going into the details of what the higher power derivatives mean. So now let's talk about derivatives of second power. So if we took, and now we're going back to our other picture here. So we're going back to this picture now. So we've talked about the meaning of the first derivative of this function evaluated at this point a. Now let's talk about differentiating it for a second time. So if we took the second derivative, and I think actually I'll go back to, whoops, what am I doing here? Oh, I didn't realise that when you undid it moved you as well. So if we now talk about taking the second derivative of our function with respect to this difference and evaluating at a, what does that actually mean? Well, it is the derivative of the derivative, so it's now going to be the derivative with respect to x as delta x is equal to s of the first derivative f prime s a, or rather x, and then I'm going to get rid of that a, we'll keep it as a general point. We're just talking about the actual value of the function rather than the value of the function at the point a. So just like the derivative tells you about how much the function is changing, the second derivative then tells you about how much the derivative is changing. It's the derivative of the derivative. And what's ingenious about this is, just like what we've just talked about, if you know the value of the function and you know the value of the first derivative, then you can work out what the function is going to be forward. You know, if you go forward by s, you know what the value of the function is going to be. If you now know what the value of the second derivative is, my claim is that you can now go forward by not just s, you can go forward by 2s, so this can be the point A plus 2s now. So you can go forward to this point, and my claim is you can work out what the value of the function is going to be at A plus 2s. So we can work this out if, my claim is we can work this out if we know what the value of the function is at A, we know what the value of the first derivative is at A, and we know what the value of the second derivative is at A. If you know all of this, my claim is you can then work out what the value of the function must be here. And the reason is, with this and this, you could work out what it was going to be at A plus s. With this now, this tells us how much the value of the derivative has to change if you move forward by an amount s. So it effectively tells us what the derivative is going to be at this point A plus s. So let me explain, or make some more space over here. So if I want to work out what f is going to be at A plus 2s, then I need to take f of A, which is the value of the function here, and then we've said already that we need to add on this change here, this vertical side of the triangle there, but we also need to add on the vertical side of this triangle here. And now we've already worked out what the vertical side of the first triangle is going to be equal to. That's going to be equal to f prime s a times s. That's what we did here. So this gives us the value of the function at a plus s. Now what we need to do is work out this triangle. Well, for that we need to know what the derivative is going to be here, because it's going to be equal to plus f prime s at a plus s times s. So just like the side of this triangle was the derivative here times s, the side of this triangle is going to be the derivative here times s, which is what this is. So how do we work out what this is if we've only got values at a? Well, this thing tells us how much this one changes to become the derivative at the next point. So it's the complete analogy of this here. So the derivative evaluated at a plus s is just going to be equal to the derivative evaluated at a plus the derivative of the derivative, which is the second derivative evaluated at a, times s. So now what we can do is just plug this into here, and then we have a formula for f evaluated at a plus 2s. So this is going to be equal to f evaluated at a plus f prime evaluated at a s plus, and then we'll fill this in, so we'll get f prime evaluated at a times s plus f double prime evaluated at a s squared. So that is a formula, and of course we could bring these two together and make that 2f prime evaluated at a s. But the point is, this is a formula for the value of the function at a plus 2s that just uses the value of the function at a, the value of the derivative at a, and the value of the second derivative at a. And then this goes on. This goes on because, you know, if you've got the third derivative, my claim then is you can work out what the value of the function would be at a plus 3s. Because for that, what you need to then know, obviously we can draw a picture here. You would need to know the side of this triangle now, so you need to know what this is. And for that, you'd need to know the derivative here, and therefore you need to know how to change the derivative from this point to the derivative at this point. And I think maybe we will actually just work this out. This will be a bit of a ache, but I think we will do it rigorously just to make sure everyone understands, or fully to make sure everyone understands. So my claim now is that we can work out what f at a plus 3s is going to be, provided that we have the information of what is f at a, what is the first derivative evaluated at a, whoops, no, that's not what I want. What is the second derivative evaluated at a, and what is the third derivative evaluated at a. As long as you have all of that information, my claim is you can work this out, and I just want to show you how you can do that. And then I'm not going to go beyond that. I hope you understand that then if you know the fourth derivative, you can work out what f at a plus 4s is going to be. And if you have the fifth derivative, it goes on and on and on. But we will just show this one just to convince you that this is going to work. So, firstly, it's going to be all of the formula that we already have, which gives us what the value at f at a plus 2s is going to be. So all of this we need to transfer up to here. So it's going to be f evaluated at a plus 2 f prime evaluated at as plus f double prime evaluated at a times s squared. And now what we need to know is what is this difference here. So for that, we need to know how to change the derivative from here to the derivative from here. So we're going to need f prime evaluated at a plus 2s times s. And for that, we're going to need to know how to change the second derivative so that we can work out how to change the derivative at another point. So just like here, where did we do it? Here, no, not here. Where is it? Here, we use the second derivative to change the first derivative, to tell us how to change the first derivative to go forward a point. Now what we need is a new second derivative at the point a plus s to tell us how to change this one's derivative into this one's derivative. And for that, we're going to need the third derivative, because the third derivative is the derivative of the second derivative. So if we want the second derivative, and I'm already wishing that I hadn't done this, at the point a plus s, then it is going to be the second derivative at the point a plus the third derivative at the point a times s. Hopefully you'll agree with that. That makes sense. If we want to know what the value of the second derivative at this next point is going to be, we just need the value of the second derivative here plus the derivative of the second derivative times s. Good. Now, this new second derivative here, we've got the second derivative at this point, is going to tell us how to change the first derivative at this point into the first derivative at this point. So, the first derivative now at the point a plus 2s is going to be equal to the first derivative at the point a plus s plus the second derivative at the point a plus s times s. Hopefully that makes sense as well. So we want to find out what this, the first derivative is here so that we can find this difference. And it's going to be equal to the first derivative here plus how much we have to change the first derivative. So we've got the second derivative evaluated at this point times s. So we can now stick in this formula for the second derivative there. So it's going to be f prime at a plus s plus the second derivative evaluated at a plus the third derivative evaluated at a times s, all of that times by s. Right, how are we getting on then? So going back up here, we've got this. This is what we need, f prime at a plus 2s. So we now just need to stick this, oh no, we need a value of this. So this is the first derivative at the point a plus s, but we already must have a formula for that somewhere. That's just going to be the first derivative at, we already must have a formula for that. That's just going to be the first derivative at this point plus the second derivative times s. Oh my goodness. Yeah, so I am already wishing that I hadn't done this. So just draw a blue line across there. And I do apologise if this comes out wrong, but you get overall picture of what I'm attempting to do here, that it is possible, if you know the first, the value of the function, the first derivative, the second derivative, and the third derivative, you can in principle work out the value of the function at a plus 3s. But let's continue on. Let's brave this. So we want the first derivative at the value a plus s, which is just going to be equal to the first derivative of the function evaluated at a plus the second derivative of the function evaluated at a times s. So I've just replaced this with this, and then we want this, all of this. So it's going to be plus the second derivative evaluated at a times s plus the third derivative evaluated at a times s squared. So that is the value of the first derivative now at a plus 2s. So we now just need to, I hope, substitute this in here. And this is the point that we hope to God that it's worked. So this is going to be equal to, and we'll do it in a different colour so it all shows up. So f of a plus 2f prime evaluated at as plus f double prime as squared plus all of this now, another first derivative evaluated at a plus 2 lots of the second derivative evaluated at a yes, times what am I doing here? Why did this one not have an s squared is what I'm questioning. We'll trust that it's right anyway, never mind. My intuition though is it should make something nicer than this, but never mind, we'll put it all in. So where were we? So f double prime s squared plus f prime s plus 2 of them times s plus, oh, of course, it's all supposed, that's why it's gone wrong. I was thinking it shouldn't look like this. Right, so we've missed out this s from here. That's what's wrong. So this needs an s multiplied on it. S. This should be s squared. And the third derivative is going to be multiplied by s cubed. So that looks plausible. Let's just put them all together. In fact, that looks very nice. No, this has worked, yes, because look how lovely the numbers have all come. So the final thing in yellow here is going to be f at a plus 3 times the first derivative times s plus 3 lots of the second derivative s squared plus, I'm very pleased with myself now, that's worked very nicely, s cubed. There you go, and you see how beautiful that is, that the coefficients are the binomial coefficients and each of the derivative terms has got an equivalent power of s. We can tell that this is right just looking at it because it's worked out so beautifully. And that is the value of the function at a plus 3s. Whew. Right, so the purpose of that was a demonstration that if you know the value of the function at a, the value of the first derivative at a, the value of the second derivative at a, and the value of the third derivative at a, that then tells you not only the value of the function at a plus 3s, but it also determines all the values of the function in between. So it tells you the value of the function at a, the value of the function at a plus s, the value of the function at a plus 2s, and the value of the function at a plus 3s. And we could go on. If we had the fourth derivative, it would tell us the value of the function at a plus 4s. And the fifth derivative and the sixth derivative, if we had higher and higher derivatives, if we knew what the value of the derivatives, and it only has to be at one point. So these are numbers, remember, it's not a formula. These aren't the general derivatives that we need. Let me get my highlighter. These things here, they're not the general derivatives, they're not in terms of x's, they're just numbers, they're the literal value of the derivative, or the first, second derivative, or the third derivative at that point A, so they're just numbers. If you know those numbers, then it automatically can be used to work out what the value of the function is going to be in the future. And the higher power derivative values that you have, the more information you know, the more points that you could in principle work out of what the function is going to be. And this is the central idea of where the Newton series and the Taylor series comes from. It is to say, for our general function here, if we could create another function, a polynomial, or a function made up of very special functions, such as these things over here, which has all these same values of derivatives as your function, then surely that thing that we're creating would have to get closer and closer to being your function, because it would be the case that it would have to have the same values at more and more points. So if I can create you a polynomial or a function which has the same values of the first derivative, the same value of the function, the same value of the first derivative, the same value of the second derivative, the same value of the third derivative, the same value of the fourth derivative, fifth, etc. And we could go on and on. If I could do that, then it would be the case that it would have to have the same value at a plus s, the same value at a plus 2s, the same value at a plus 3s, and you can see that that means that these functions are going to have to get more and more similar because they're going to have to intersect at all these points. So you can imagine having another function here, and if they had the same values, if this function in red had the same value at a and the same value of the first derivative at a, the same value of the second derivative at a, and the same value of the third derivative at a, then it would be the case that it would have to intersect here at a plus s, and here at a plus 2s, and here at a plus 3s. And the more and higher you go on, so if it also had the same value of the fourth derivative and the fifth derivative and the sixth derivative, it's going to have to go through points in the future as well, and you can do more and more points, and you can see that, you can imagine that this line, this red line, would have to get closer and closer to being the same function as the white line. And that is the premise on which this series is constructed, that if we create this new function that has to have the same values of these derivatives at a point, then that function has to get, the more and more we add on, the more and more of the derivatives we make it obey, and we make the same as our function, the closer and closer it's going to have to get to being our function. So we'll have a break here, and in the next video we'll expand that concept and actually derive the Newton series, but in our notation rather than the official notation. And then we'll see how it becomes the Taylor series as you let s shrink to 0.